All right, everybody, welcome back. Today what we're going to do is we're going to work on graphing rational functions. So in order to do that, we need to keep in mind some of our key characteristics, which we are going to talk about first. Now, if you look at this as one big picture, it's a lot of work to try to memorize where each of these things is going to come from. So instead, what I suggest is trying to understand what each of these things are, and that should help determine where it comes from. So for example, if we are thinking about our vertical asymptote, a vertical asymptote is a line that our function cannot cross. It's something that can't happen. So think about, okay, what in a rational function can't happen? Since a rational function is a fraction, we can't have our denominator equal to 0. So if we set our denominator equal to 0, we can find those lines that we cannot cross, those x values we cannot plug in. Now, our horizontal asymptote is essentially what's going to happen really far to the left and right side of our function. It's our end behavior. Now, to determine where that comes from, I like to think about it as us looking at what we call the most dominant terms. It's the values in your numerator and denominator that have the highest exponent. And now there are a couple of rules that we're going to talk about when we look at our horizontal asymptote, but what that is going to involve is us looking at the degree of both our numerator and denominator. We'll talk about that a little bit more specifically in a second once we see our example. Next, we have our domain. Well, the domain is basically what x values can we plug in. And for rational functions, it is always going to be all values except our vertical asymptotes. And again, those are the numbers we can't plug in because they cause our denominator to be 0, which means our function is not defined there. Now, for our range, it gets a little bit complicated because it kind of depends on the function. If we are looking at a more simple rational function, then typically our range is going to be based on all real values except our horizontal asymptotes. But as our functions get a little bit more complicated, sometimes we have parts that, go through all values, including our asymptotes. So this is something that's going to be determined depending on the situation. Now, y-intercepts and x-intercepts, we've talked about these before. You've graphed them before, so we should know where they come from. A y-intercept is where our function crosses through the y-axis, where x is 0. So if we set x equal to 0 in our function and we solve, we find out what our y-intercept would be. An x-intercept is where the function is equal to 0. So because a rational function is essentially a fraction, for a fraction to be equal to 0, just the numerator needs to be 0. And therefore, if we set our numerator equal to 0, we can find that x-intercept. So we're going to talk about these specifically with this example below. We have p of x is equal to x to the second power minus 3x minus 4 divided by x squared plus 2x minus 8. Now, as we talked about above, an x-intercept is where we set our numerator equal to 0 and we solve. So if I take my numerator and I set it equal to 0, we see this is a quadratic, and therefore I can use quadratic formula, or I can factor. So I'm going to factor this, and I'm looking for two x values that multiply to -4 and add to -3. It will be -4 and +1. So if I set each one of those equal to 0, I get my x-intercepts. So I have two of them in this point, and I have -1 and +4, that's 3, +4. The y-intercept, as we discussed, and you know what I'm going to do actually? Our x-intercept comes from the numerator. So I'm going to highlight both of them together. Our y-intercept is going to come from the entire function in setting x equal to 0. So I have 0 squared minus 3 times 0 minus 4 divided by 0 squared. I believe it's a plus 2 times 0 minus 8. Yes, it is. And this is going to simplify to negative 4 over negative 8, or really just 1/2. So my y-intercept is 0, comma 1/2. Now plot that in orange, and it is right there. Next, we have our vertical asymptotes. The vertical asymptotes are going to come from setting our denominator equal to 0. So I'm going to highlight my denominator, highlight my vertical asymptote, and solve for the denominator. X squared plus 2x minus 8 is equal to 0. Again, it's a quadratic, so I can factor. Technically, I can take the square root 2, but because there are two different x values here, an x squared and an x to the first power, I can't do that. And I'm going to factor this as well. And I need two numbers that multiply to negative 8 and add to 2. That's a positive 4 and a negative 2. So by setting each one of these equal to 0, I get those asymptote equations. So I've got negative 4 and positive 2. And now my function's starting to take shape. So we can see here that because I have two vertical asymptotes, there are going to be 3 sections that I'm going to have to graph in. Now that horizontal asymptote is going to help us out. And to determine what our horizontal asymptote is, I look at those leading values, the values with the highest degree in both my numerator and denominator. So I am going to take my x squared and divide it by x squared. And because those degrees are the same, that tells me that my asymptote is going to be y equals whatever the leading coefficient of my numerator is, which is 1, divided by the leading coefficient of my denominator, which is 1. And 1 over 1 is 1. So now I've got my horizontal asymptote, which I will, I guess, do in orange here. You know what? I'm going to do it in black instead. Is at positive 1. And this is going to help me out with my end behavior at the end. So we now have really enough information to graph our function. If I do this, I know I need to go through each of these points. So if we start off in the middle, I'm going to connect these two values, and then I'm going to follow the trend that it's going. Since I'm going up from left to right, I'm going to continue to go up. And remember that functions like to hug asymptotes. We get very close to them, sometimes without going through, depending on if it's vertical or horizontal. And then our trend will continue to the left and down, and that's what our middle section is going to look like. Now, what happens at these asymptotes is since I'm going up on the left side, on the right side, I'm going to be coming from the bottom. So it's going to look something like this. It's probably not the best drawing, but we do get the idea. And the same idea is going to happen over here. Since I'm going down on the right, I should be up on the left, and it's going to look something like this. And that's a pretty accurate graph of what our function is going to look like. So I can do my domain and range now. And this is what I actually wanted. I want to connect my vertical asymptote and my domain. The reason that is because my domain is going to be all values except those vertical asymptotes. So it's going to go from negative infinity to negative 4. That is this section of my graph. And then I hit that asymptote and I almost jump over. So then we're going to switch from negative 4 all the way to 2, which is that middle section here. And then again, we get to 2 and we jump over to the other side. So we're going to have 3 parts of this domain. And I am going to put a union symbol in between. So it says this section and this one and this one. Finally, I want that range. And this is why I said it kind of depends on the situation. If we look at this one on the left and the right side, we don't really pass through that asymptote. However, in the middle, we do. And so we go from all the way to the bottom to all the way to the top. So our range here is going to be from negative infinity to infinity. Now, the last part is our end behavior. And remember, end behavior always starts the same way. As x goes to infinity, our function, which is p of x, is going to go where? And then as x goes to negative infinity, our function p of x goes where? Well, we can really get this by looking at the graph, but remember that it is actually coming from a horizontal asymptote. That is the importance of a horizontal asymptote, is it tells us where our function is going very far to the left and the right, which is end behavior. So as we move to the right side, our function starts to go up, 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 and then we kind of level off as we get close to that asymptote. But it doesn't really look like we go through, but we start to approach that asymptote, which is at 1, actually. Sorry, not 2. Is at 1. And actually, the same thing happens in the other direction as I go towards negative infinity for my x values. As I'm moving this way, we start getting closer and closer to our asymptote, but this time from above. So again, our end behavior is going to go towards 1 when we move to the left. So this is a pretty good example for us to look at. It is a little bit more complicated because we need to essentially factor and solve quadratics in both the numerator and denominator, but it's a really good problem to do because it allows us to see, how difficult these problems can get. All right, thank you for listening, and as always, if you have any questions or concerns, please feel free to reach out and leave a comment below. Thank you.